The 1990s was an exciting time with some of the most important political and cultural events in world history. It was a time of rapid technological progress as well. For example, dial-up modems allowed young men to chat with babes online all day. Well, at least, we thought they were babes. There was other stuff going on too, though. MRI scanners were becoming faster and more affordable, and researchers were investigating how the brain responded to different stimuli. But what if the subject was doing nothing at all? In 1995, a man named Bharat Biswal scanned subjects when they were doing a task, in this case, pressing buttons at a certain rhythm, and also when they were simply resting, a condition called resting state. To his surprise, even after removing from the resting state data all physiological sources of noise he could think of, some kind of signal remained. Biswal then decided to extract the time series from the left motor cortex and correlate it with every other voxel's time series. Instead of the random correlations that one would expect, there was a strong correlation with the opposite hemisphere's motor cortex, suggesting that these two functionally similar regions, although physically distant from each other, generated similar patterns of activity even at rest. The following demonstration will give you an idea of what he did and what functional connectivity is. We'll use FSL for this demonstration, which you can download from the link below. You will also need to download the sample dataset, which can be found here. To examine the time series of the sample dataset, navigate to where you downloaded the file and type fossilize time series example data.nai.gz. This will open the file in the fossilized viewer. From the menu at the top of your window, click on View Time Series. This will open a time series panel at the bottom of the fossilized viewer. To scale the numbers relative to a mean of 0, and therefore make it slightly easier to read, click the Plotting Mode drop-down menu and select Normalized. Now, click on a random voxel anywhere in the brain, and then from the menu at the top of the screen, select Tools, Seed Correlation Pearson. The voxel you've currently selected will be a seed voxel. The time series of this seed voxel will be used as a reference. This will generate a connectivity map between your seed voxel and every other voxel in the brain, with hotter colors representing greater correlation. Click on the plus sign to keep this time series displayed, and also change the color. In this case, we'll change it to red. When you click on another voxel, its time series will be displayed in blue. This way, you can see how the time series of your seed voxel correlates or anti-correlates with the other voxels. You will also notice that a new file in the overlay list has been created, time series example data/correlation. If you highlight this image by clicking on it, you can then set the min and max thresholds to only show those voxels that correlate with the seed region at or higher than a certain level. Let's set the min threshold to 0.3 and take a look at which voxels remain after we set this threshold. Before moving on, click the minus sign to remove the original seed voxel's time course. Now let's see whether we can replicate one of the most well-known functional connectivity networks, the so-called default mode network. This network is a pattern of correlated regions, primarily the ventromedial prefrontal cortex and the posterior cingulate cortex. To find this network, use the voxel location fields and enter values of x equals 32, y equals 53, and z equals 16, and use this voxel as a seed for another functional connectivity analysis. You should see two large clusters that are correlated with each other. In other words, we've uncovered the default mode network. Now, to replicate Bharat Biswal's 1995 finding, let's try placing a seed in the left motor cortex, which is roughly in this area, 42, 31, 30. correlation analysis reveals what is called the motor network, which is another robust network that we can find in virtually anyone. Click on the link below for a list of other networks and try to find them by using this correlation method. Now that you have an idea of what functional connectivity is, you're ready to begin using the Conn toolbox. In the next tutorial, we'll find out how to download it, how to install it, and how to start looking at some data. All of that and more once I get my dial-up modem working again. And yes, this is what it sounded like. Two squirrels molesting each other. The data we'll use for this tutorial comes from the open access repository openneuro.org. From the OpenNeuro homepage, click on Public Dashboard, and then use the search bar to look for the string arithmetic. It should be the first result that is returned. Click on it, and then for now, we will download one subject to analyze. Click on the sub01 folder, and then click on ANAT. Click the download button next to the file sub01t1w.nai, which will begin downloading the file. Next, click on the func folder to look at its contents, and download the file sub01 task rest_bold.nai.gz. If these files have been downloaded to your downloads folder, open a MATLAB terminal and then type the following: cd desktop and then mkdir conn_demo. This navigates to your desktop and creates a new folder called conn_demo. This is where we will put our data and do our analyses. To organize the data into two folders within the conn demo directory, type the following from your MATLAB terminal: cd conn_demo makedir sub01/func and makedir sub01/anat, which will create the folders func and anat within a folder called sub01. To move your downloaded files into their corresponding directories, type the following: move file, single quotes, tilde, downloads, the name of, in this case, the func file, then a comma, sub01/func. And we'll do the same thing for the anat file. Once you've finished doing that, type ls sub01/anat and ls sub01func to make sure that the functional data is now located in the func directory and that the anatomical data is located in the anat directory. If so, you are now ready to begin using the Conn toolbox, which we now turn to. The Conn software package is what is known as a toolbox, a suite of commands designed to be used as an add-on to SPM. The Conn download page can be found here on the NITRC website. Simply click on the download button to begin downloading version 19.c. You can also find a link to this web page in the More Info box down below. This download will take a few minutes, so we'll fade out and come back. When it has finished downloading, unzip it. This will create a folder called Conn in your Downloads folder. Then open a new MATLAB terminal and type move file, single quotes, tilde, downloads Conn, comma, and single quotes, another tilde, which will move the Conn folder to your home directory. The next step is to set a path to the directory so that we can access the Conn toolbox from any directory. Click on the Set Path button and then click on Add Folder. Select the Conn folder from your home directory and then click Save. Then click on Close to return to the MATLAB terminal and simply type Conn, C-O-N-N. If the path has been set correctly, Conn should load. And after a few moments, you will see the default Conn screen, which looks something like this. If you see the Conn home screen, then you have both successfully installed Conn and SPM. If you don't have SPM installed yet, click on the link in the More Info box down below. We are now ready to begin our tour of the Conn GUI and explore some of the options in more detail.